Well, greetings and welcome back, class. In this video, we're going to talk about a concept called Makefiles. Makefiles build upon what we were looking at in the previous video. In the previous video, we discussed the different steps that take place when you're compiling a program, such as a C program, to be a little bit more specific in this example. And we looked at the various stages going from C program to assembly language, machine language, linking multiple different object files, machine language modules together from different libraries into a single executable, and then having those loaded into memory. And now in this video, we're going to, with the concept of Makefiles, is we're going to learn a bit about how we can manage this process in a more automated way in which the rules of compiling a program are specified in a single place, and we can use this we could specify the rules that we desire to compile a program. And this is typically called, the way that we do this is we're going to use something called Makefiles. Okay, we'll talk about the advantages of using Makefiles in just a moment. I think what makes this a little bit more clear before I even mention these is to show an example. Okay, so let's look at an example here. In the example I'm going to show you, okay, this example, first, let's just take a look at the files that are in this folder here. I did ls, display all the files that are in this folder. I have 3 C files, right? 3 source files, main.c, assembler.c, and parser.c. And then I also have 2 header files, assembler.h and parser.h, okay? And if I do make, right, we're going to run what's some rules that are in this make file, because we also have this make file here. We'll open that up. We'll look at what it is in a moment. But for now, I want you to see it being used first, and then we can examine how to actually build one. Okay. So when I run make, there's some rules that are in that file, and we can see these steps that are taking place. They build upon what we saw in the previous video. The first 3 steps take each one of these source files, one at a time, and goes through the compiling and assembler steps to generate 3 different object files. 3 different object files. Okay? Those are the first 3 lines here, right? The -C does that. It's telling the compiler to go up through the assembler process, but not to link anything. To not run through the linker. And the last step here runs through the linker. It takes all of those machine language object files that were created from the past 3 lines. It links them together in a single executable, and it gives the executable a name that we're calling assembler. Okay, so this 4th line here is doing this step. It takes the 3 modules, object modules, machine language modules, combines them together, links them together into a single executable. I can now run that executable. Okay, and when I run that executable, this is just an example. This executable is actually a C program that actually acts as an assembler. Just an example, right? It allows me to give some sort of assembly instruction, and it will convert it to the corresponding 32-bit machine code represented in hexadecimal. So it's just effectively that last step. It's not really that important. I'm just showing actually executing the executable that was generated. Okay. Now, if I do ls again, we can see there's a whole lot of new stuff that shows up, right? Those object files, right? If I do ls and we just print the object files, we could see that these were generated when I ran the make file. Okay. The other thing that was generated when I ran the make file was obviously the executable too, that we named assembler. Okay, you can name it whatever you want, right? Anything after the -o is the name of the executable. And if I do something called make clean, it gets rid of all of those temporary files. It got rid of everything that was generated when I ran the make file. Right? It got rid of, if we look at ls again, all the object files are gone now. They were removed. All of everything ending in .o, as well as the executable, the assembler file, were removed. So make clean kind of clears out all those temporary things, or all those things that we might want to get rid of, so that we can recompile completely fresh. Okay. So you might start by doing this example of just seeing a Makefile in action. You're probably getting a little bit of a sense of some of the big advantages of using it. Okay, a big one is simplicity, right? Real world, you can get get really complicated programs that are just having lots and lots of different dependencies and different ways of compiling things. So it makes it easier, right? You type in one word make, all the rules about how it should be compiled are contained within the file, the make file. Similar to that is the encapsulation, isolating all the rules for compiling in one place. Okay, you don't have to be hunting down and looking at how you're supposed to compile something. It's one location, specifies all of it. Okay, and one thing that we haven't really seen yet, I can show you right now, is something called speed. We compile only what has changed. Okay, if I come back here, let me compile this again. Okay, it compiled everything, right? It compiled and created those object files, then linked them together. If I run make again, the only thing it ran here was the linker, because the other aspects didn't change, and we can actually build the make file in such a way that there's nothing occurs, right? There was nothing that changed during the process, and it would basically say everything's up to date. Okay, so you're only compiling what you need to compile, and we could take a look at the rules in here to see why that actually still did the linker step. It actually didn't need to, right? Because if it's already been compiled and we change one thing, I'll show you this, right? I'll open up. Imagine I'm going to change one file here. I'm going to go ahead and I'm just going to open up this something in assembler.c, change the file, hit Control-S to save it, and then run make again. Okay. Notice it did that extra step here and then linked everything together in an executable again, because that file had changed. We needed to recompile that object file and then link it back into the executable. Okay. So in terms of speed, compiling only what has changed, what you need to. If you have it's not as important as it used to be when you had really complicated, massive systems and computer performance wasn't as powerful it is now. But that being said, it's still, if you've got an awful large system, right, and you only really want to compile what has been modified, it makes a lot of sense, right? We don't want to start recompiling all of the libraries and things that have not changed. It's unnecessary. Okay, so let's look at how to build one of these things. Okay, and what I'm going to first, I want us to just reflect. I'm going to look at how it was built for this last example, but I want us to reflect a little bit on the files that were in there. We've got these 3.c files, the implementation, source files, the implementation, and then we have the 2 header files, the interface. Okay, and let's take a look at those. And if I open them up, I summarized it here, but if we open up, for instance, main.c, you notice that I'm ignoring the system libraries, but notice that includes parser.h and assembler.h. I'm just including those includes here so we can get a sense of the dependencies, right? While assembler.c included parser.h and assembler.h, okay? And parser.c just had parser.h. Okay, so we're getting a sense of the dependencies by looking at that. We're getting a sense of the dependencies. And this is really important. Okay, this is really important because what we want to get towards here is we're trying to make files follow the following format, right? Where we're listing all the dependencies for something, right? You'll see this in a moment. We take, for instance, something that needs to be done, right, or some sort of commands that should run, and we list the dependencies that need to take place for running those commands. So that, for instance, if any of the dependencies change, we want to redo this. We need to run these commands. So if we look at this, right, we could actually build some sort of little visual framework for analyzing this based on these rules that were specified here, right? We know that these are what's included where. So let's look at these. Let's try to graph or draw something that indicates these dependencies based on this information here. Okay, so if we look at the relationship between these, right? If we for instance, draw maybe the header files up here, and we have the assembler.h, right? We have the parser.h, and we know that the assembler .c file depends on that, as well as the main .c file depends on that. Okay. These also have a dependency on that file. Okay. And then I'll mention a little bit more about what the dependencies mean in just a second. Let's just include the last one, that this .c file included that .h. So what I did so far is just indicating that which header files are included in which program. And what we're really kind of getting at is that if this file here changes, this header file, we know that we better change this, that we better recompile this and this, okay? Because there's a dependency there, right? If you change the interface of how that which is specified in that header file, right? That means that we need to recompile, because the interface is really what matters when you're kind of including something together. So for instance, if you had something like a power function in that library and you change the name of that function, right, that's going to impact files that are using that library, right, that information that was specified in the header file. So you better recompile. Okay, so we know that that there's those dependencies there, and what we want to do is we want to basically lay out the different dependencies, so that we know that, for instance, if we take the main object file, right, and when we're going to compile the main object file, we know that that object file depends on the main.c file, right, as well as the assembler.h, okay, and the parser.h. Okay, so what that's saying is we know that if to recompile this main file, right, this main object file, the machine code that comes from that should happen if this changes or either one of these header files changes, okay, because those are the interface, right? However, you could change something in the assembler.c and not need to recompile the main object file, right? The reason why is, right, we've separated interface from implementation. If you change the assembler.c file, but that change does not impact the interface, we don't need to recompile the main, the main object file, right? Because the interface remains the same. How they're going to work and work together remains identical. Okay. Assembler.o, likewise, that depends on the assembler.c file. Okay. The assembler.h, okay, as well as the parser.h. It uses that library, the parser library. Okay, we could see that there. If this needs to get updated, that object file, if the assembler.c changes, the assembler.h or the parser.h. And then lastly, the parser, that needs to get updated. That if this one's a little simpler, if either the parser.c or parser.h are updated. Okay, and then lastly, we need to run the linker step. Okay, the linker step needs to be updated if any one of the object files changes. Okay, if any of the object files change, we need to relink everything together into a new executable. Okay, so this last step here is really the linker step. Okay, and this is one reason that this is helpful to learn this, beyond just having a conceptual understanding of how computers work, which is important in itself. You do get errors at times that will say something like linker error or have a clue that it's a linker error. It gives you a better understanding of how to kind of fix certain problems by understanding the different where in the process it may have failed. Okay, so we've got this. We've specified these rules. Let's take a look now at a real Makefile. Okay, so here's a Makefile. And what we have here, okay, is we've specified these different steps along the way. Okay, we've specified what's really going on here is we've got as we talked about, there's the target and then there's the dependencies. So what we're saying is the main.o, that target, that depends on any of these that change, we should run this command. You could have more than one command listed. We're just listing one. Okay, so if any of these change, we should run this command, right? Recompile to generate the main object file again. So these are just using the rules. If any of these change, right, this file, that object file depends on it, we're going to run this. Okay. Now, Makefiles are really annoying in the context of this really needs to be a tab. That's a super easy mistake to make. They're really picky. Some of it dates back to just how these things, how people originally built these things many years ago, and the conventions have stuck. But the key thing is just making sure you're remembering we're listing the target, the dependencies, and the commands. Okay, and you're listing them out. Right, this top one here, and I'm going to change the name of this. I'm just going to call this assembler because it's the name of the executable, or we could even call it, if we wanted to keep the name executable, I might just change that so that we're going to change the name to executable. Okay, what that's saying is that if any of these files change, okay, if any of these object files change, right, the executable depends on those, right, we need to rerun the linker. We need to rerun the linker, right? We need to relink all of those machine language object files into a new executable, okay? And this last rule down here, just the clean steps, a good thing to have is if you want to just wipe everything that was generated through running the Makefile, right, this is just getting rid of all the object files and the executable, right? And again, I could change the name of the executable, anything after the -o, and change the name of the executable. But I just call it this just so you can kind of see clearly what it is in this case, right? So if I run this again, right, notice if everything is, let me kind of show that again. Let me clear the screen. Let me run make. Okay, notice it said the executable is up to date. Okay, I'm going to run make clean. I'm going to wipe everything, all the temporary stuff, the object files and the executable. Okay, I'm going to run make again. Okay, regenerated all of those. Okay, now that if I run make now, since we just ran it, we didn't change anything. Notice it tells me it's up to date, right? It doesn't have to recompile anything or run through the linker again. It's all up to date. Okay. However, if I go and I make a change, right? If I make a change, for instance, in main.c, I'm just going to go here and hit space and save, right? Just so it looks like that file's been updated, and I run make again, right? It recreates the main object file and then relinks everything into an executable. Okay, so it only recompiles, right, and links things back together that it needs to. Okay, so that's one way in which it's optimizing it. If you have hundreds and hundreds of files, right, that's very helpful. You don't have to constantly be recompiling everything if you're specifying the rules correctly in the Makefile. Okay, we'll get practice as we go through the class. We will use these as part of building some stuff. Right? It makes it helpful, both for you to keep yourself sane, specify the rules in one place. It's also a great way of sharing what you've built with other people, because you can just be like, here's the code, here's the Makefile, and someone else can replicate and recompile what you did with no additional instructions. Okay. All right, so we'll wrap it up there. We'll stop the video at this point. Feel free to email me with any questions, and otherwise, I'll see you in the next video.